So this video is called Memory Management in Java. This is not presented in your book, but I think this is a very important thing for you all to learn, and it may help clarify lots of things that we're going to be coming up with as we start studying dynamic data structures. So I want you to consider this very, very simple Java program that I've written here. I start off, I have a public static void main. I declare a couple of variables in here. At some point, I call a static method called floopy. So I come down here. Here is static void floopy. Again, I declare some variables. Someplace in the middle of this, I call something called guppy. And here's guppy down here. And you can see this is a mistake. This shouldn't be here. So let me cross that out. Let me do a cancel here. That doesn't exist. Otherwise, I'm making recursive calls, and we don't know what recursion is for another week or so. Okay, so this in the middle of this one, it calls this one. In the middle of this one, it calls this one. This one will execute all the way to the end. When it's done, it comes back over to here, to the line after guppy, until this comes down and this ends. And then it's going to come over here. It's going to come down like that. Now, what I want to consider here is I want to talk about what's happening in memory when all of this is going on. And we're going to be drawing several pictures. This is a pretty simple picture. And let us imagine that you started executing this program, and here is all of the computer's memory that has been allocated for your program. So again, we realize that this is just a piece of memory, that there's other things going on in memory. Maybe you're playing some music at the same time you're running this program. You could be doing lots of other things. But over here is your program code. And that's in here. And that's occupying this space up here. So what's happening over here is we have a lot of free memory, and this free memory in here is going to be used for your program variables. Now, the Java interpreter actually breaks these things up into two pieces. Over here, there is something called a heap, and the heap grows this way. And what's way down here is something called a stack. And the stack grows this way. And you may wonder, is there ever a problem of these things crashing into each other? And yes, that is a problem. It doesn't happen very frequently these days in the world of virtual memory and computers with gigabytes of RAM. But years ago, programs would actually crash if these two things ran into each other. The other thing you might be wondering, we've learned about this thing called stack, a stack, a data structure called a stack, and here we're using the word stack, and you have to wonder, is there any similarity? And the answer is yes. We're going to see that we basically push things onto this thing, and then we pop them off. Likewise, you're going to see that the heap actually behaves like a stack as well, but it's growing in the other direction. We push things onto the heap, and the heap will go down this way, and when we remove things from the heap, they go back this way. So the idea here for this sample program is very simple. First of all, I want you to notice that in all three of the methods here, I'm only declaring primitive data types. I'm not declaring any objects. We'll do that later on in this video. But the idea here is very simple, that when I come over here and I start executing static void main, I'm going to come over here to the heap and I start exercising, and I'm going to call this main.a. Because it's a primitive data type, that just means I put the number 23 in here. And then I'm going to come over here, and there's going to be, I'm just going to call it main.b. And that's going to be my 56.89. And then there's going to be main.c. And what's going to happen in there is that is the character X. And I come along here and I start executing, and now I come to floopy. and I come down to floopy, and now floopy declares some variables. So this is going to be floopy.a, and that's going to have the value 23 in it. It has nothing to do with this 23 over here. And likewise, there's going to be my floopy b, and floopy b is going to be 56.89. And again, that has nothing to do with this one over here. And now I'm going to call it floopy c. Over here, I call it floopy underscore c, just to indicate that it is in fact. And there's a y. And I come here and I execute some code, and right down here in the middle, I execute guppy. So guppy comes down here, and guppy has an a. And again, that's the value 23. And then there's a guppy b, and that's a 56.89. And then there is a guppy c, and that is the character y. Okay, so this is what my heap looks like at this point. Now when I come down here and I hit this closing bracket, what I am going to do is I'm basically going to pop the heap. And I'm going to pop the heap of the variables that got allocated here. So what's going to happen, basically it's a pop. These guys go away. Actually, I can even get rid of these lines here. Pardon the mess, but I think you all get the idea. And now what I've done is I have these three spots that were previously used for the variables for guppy are now available should anything else be required on the heap. So these guys are gone. And of course, since I've hit that closing bracket over here, I now come back up to here, and I continue with my execution of floopy, and floopy keeps going until I hit this closing brace, and now these guys are going to go away. I'm popping the stack, I'm popping the heap, I should say. So these guys are now gone, and I'll get rid of these. And finally, I hit this closing brace over here, and I come back up here, and I pick up execution right over here, and I go all the way down until this program ends, and when that program ends, not only does this get completely freed up, but in fact everything gets freed up. What do I mean by everything? Once your program has terminated execution, the memory from here all the way down to here will get freed up. Okay, so the point that I'm trying to make here so far is that when we have primitive data types, when we allocate them, they get allocated on the heap. The heap keeps growing. It grows like a stack. And the point is in whatever method they are declared in, they go away as soon as that method is over. You've seen something similar to this. For example, if I do something like this, if I say for int I equals 6, or for int I equals 6, well, I is less than 12, I plus plus, and I come over here and I open some brace and I close some brace. This int I only exists for the time that that's executing. In other words, I will go onto the heap, I'll create a new value for I, and when I get down to this closing brace here, I'm going to be popping the stack. I'm going to be popping the heap. Okay? Part 1 of the video. Now we'll do part 2. Okay, let's consider a different scenario here now. And let's take a look at this code over here. First of all, we will note that we've defined two classes here. So we have a public class GUI. Nothing very interesting about it. A couple of instance variables in it in here, and then some methods, constructors, whatever. The same thing for FUI over here. Again, nothing very interesting. But here's my public static void main. I declare a variable. I declare an instance of a GUI. And then I call this thing called my method. And in my method, I declare some more variables here, including a primitive data type, and then two instances, one each of these classes here. And again, what I'd like to talk about is what is the picture of memory as all of this is going on. So let me draw a picture of memory. And I'm just going to draw the picture of the heap and the stack. So over here is the heap. Over here is the stack. I start executing this program. So the first thing is I've got this variable over here called AA. And I'm going to call that main.aa, just so that we know where it comes from. And that's got a 56 in it. Okay, so now things get interesting. And what I'm doing here is I am creating an instance of GUI. Now the first thing is this variable myGUI, that gets allocated over here. So here is m.myGUI. But what happens is it's this magic word new that says go to the stack, and it says create me an instance of a GUI. So it's going to come over here in the stack, and it's going to go, aha, here we go. I can do it right over here. And in fact, if I come over here, here's where the variable x will get stored. And here's where the variable y will get stored. And who knows, maybe there's some other stuff over here. Now this corresponds to an actual memory location. And maybe this memory location, and I'm just making this up for now, starts at location 5000. That's actually what gets returned by this call to new. And what happens is over here, I record the number 5000. Now diagrammatically, we often draw this way. We say that this references here. But that's just another way of saying that I have the memory location here stored of where this thing begins. And it looks like I called a constructor, and it says, oh, I probably put the number 45 in here. And I probably put the letter S in there. Okay? And now I go on my merry way, and I come over here, and now I'm calling my method. And in my method, let's see, there's a variable called bb, and I'm going to use a lowercase that, m.bb. And what I've done in there is I've put the number 56. And now I'm creating one of these GUI things again. So what's going on is first of all, over here, I have lowercase m dot myGUI. And what is going on here is now I need to go down here into the stack, and I need to find some more free memory, and maybe I find it over here. Maybe it's location 4000. And I'm creating another one of these GUIs, so there's going to be an X. There's going to be a Y. It looks like I'm calling a constructor. It looks like I was too lazy to type in different values, but it's a different 45. And it's got the value S. And what's happened over here is this is going to have the number 4000 in it. And this, we could draw a picture to represent, would look like that. Now I'm going to come over here and I'm going to create a fooey. And I have my foo. So that is m.myfoo. And that's going to be here. And I've got to come over here someplace, and I've got to find, again, space in the stack for it. And maybe it's over here at location 3000. And here there's going to be a private int A. There's going to be a B. It looks like I've called a constructor here. I've put a 78 in there. I've put an M in here. 3000 gets returned, which means I've put a 3000 there. And this looks like this. Okay? So here's what memory looks like when I'm at this point in executing the program. And now the question is what happens when I get down to here? What happens when this gets encountered? Well, the answer is that the corresponding variables that were declared in this method get popped off of the heap. So what's going to happen is my foo, my goo, and bb are going to disappear. So these guys are going to go away. So this is gone. This is gone. And this is gone. And I'll try and get rid of those lines as well, just to make this look a little bit cleaner. They've been popped off of the heap. And these references, once that method ends, these references here to these variables don't make any sense. They go away as well. And you might be wondering, now what happens? Particularly, what happens to this thing over here and this thing over here? Because now execution is going to go from here back up to here. And the answer is this stuff still remains on the stack. Okay, it's still there. And the big question is, does it ever go away? And the answer is yes. But as we can see right here, it doesn't go away right away. What happens is the Java interpreter every once in a while stops what it's doing and it does something called garbage collection. And what does garbage collection mean? Garbage collection means that it needs to go into the stack and it needs to look for any memory that isn't being used anymore for anything and deallocate it. Or in other words, pop it off the stack so that we can use it again. Well, how does it do that? Well, what it does is it looks to see if there are any references to it. For example, it comes over here and it says, well, there's a 3000 over here where I've started to use stuff. And it goes back into the heap and it goes, is anybody referencing 3000? And if no one is referencing 3000, then this stuff gets cleared up. Comes over here. It says, is anybody referencing 4000? And it comes over here and it says, well, nobody is currently referencing 4000. So what I'll do is I'll clear it up. It sees a 5000. Is anyone referencing 5000? And the answer is yes. It sees this here. So it says, I'm going to leave this alone. So the question is when does this happen? And I'm going to just say periodically. Okay, which means it doesn't happen every 3 days. It probably happens much faster than that, probably on the order of seconds, if not microseconds or milliseconds. But whatever is going on is whatever the Java interpreter is doing, it stops. And it says, okay, I've got to look for these numbers here and see if they appear anywhere in the heap. And if they don't, then what I need to do is just go ahead and deallocate this stuff. Just want to bring up one more point here, and then we will end this particular tape, and I hope it's been instructive. We haven't talked about recursion yet, but I know that you all saw it in CS2. So I want you to consider something like the following. Suppose I came over here and I had a public static int, and I'll just call it f int n. And I'm going to come in here and I'm going to say If n is greater than 0, return n times f of n minus 1. And you should recognize all that. This just looks like factorial. And I want you to consider something else. I'll call it f2 int n, and I'm going to come in here and I'm going to say something like the following: int and my data equals new int. Oh, why don't we make it big? 50,000. And then I come over here and I say something like the following: if n is greater than 0, return n times f of n minus 1. Okay, now these both do it, they calculate exactly the same thing. The only thing is this one, every time I call it, it declares an array of 50,000 integers. So I want you to consider what happens if I come over here and I say that a is equal to f, oh, I don't know, of 50. And I come over here and I say b is equal to f2 of 50. And I think you can see what the difference is. We can see that either one of these is going to cycle around here 50 times. Okay, but what's going to happen over here is every time I cycle around 50 times, I'm allocating an array of 50,000. Okay, 50,000 integers of 4 bytes. So this actually creates this takes up 200,000 bytes every time I call it. And by the time I got to the 50th time, I am using up a lot of memory. In fact, how much memory am I using up? It's going to be 50 times that. That's 10 million. That's a fair amount of memory to use up. Although our computer could probably handle it. The point that I'm trying to make, we are going to be studying recursion shortly. You want to be very careful when you write recursive methods about what data you actually declare inside of the recursive method. You declare some big data structure. Remember, you have the possibility of using up a lot of memory.